All right, so you guys have started looking at circular motion stuff, and we're going to look at some of the other properties and attributes of circular motion and how certain things work the way they do. So here we're just going to start with a really, really simple picture and diagram. Basically, we've got an object moving in a nice circular path, no big deal. It's at location point P right now, and that's it. We've got the R for the radius. And we've got the v vector, that's the velocity vector, and the velocity is always tangent to the circle. So that velocity, whenever something is moving in a circle, the velocity is always tangent to the circle. Okay, all right. And that's basically the first picture right there. Now let's move on to the second picture. Now, in the second picture, what we've had is the object has moved from point P to point Q. So our little object has moved from one place to the other, okay? And that's all it is. So what we've done is we've moved from P to Q. And the 2 points are totally arbitrary. It doesn't matter which ones where it doesn't make any difference. Now, of course, this, in order actually for this to happen, this took a change in t to actually occur. Of course, it took time, and of course, it also made a change in the angle. So the angle changed as it swept from P to Q. Okay, so and again, these two things are arbitrary. Technically, what you want to do is you want to technically make the delta time infinitely small, which would then bring the two things really close together. So we are going to make the change in t like very small. Like we're going to actually make it like approach zero, like infinitely small type thing. So we're going to make that delta t very small, which of course then the delta theta would also become very small. And the 2 points would pretty much be on top of each other, but we're not going to draw it that way because it'll be pretty much impossible to see. We're just sort of draw like an exaggerated version so we can actually see a little bit what's going on. Now when we do that, we actually end up creating two similar triangles. So what I've done is I've moved the two arrows sort of on top of each other, even though one belongs in one corner, one belongs to the other corner of the little green triangle. I'm going to draw them sort of where they would be like infinitely on top of each other, just spread them apart so you can actually see a little bit what's going on. Now, when I do that, I actually am able to create two similar triangles. I actually create two similar triangles when that occurs. One is like a V triangle and one is like a D triangle with the radiuses and stuff like that. So I create two similar triangles, and this side on that triangle matches up with this side on that triangle. So actually there are two isosceles triangles. So if we do that, since these two triangles are similar to each other, all of their proportions are going to be equivalent to each other. So the ratio of the sides will always be equal to each other, because that's what similar shapes do, is when you take the ratio of their sides, they're equal. The triangles can be bigger or smaller, but the ratio of the sides will always be similar to each other. It'll be the same ratio. So because of that, if I would take the change in V and divide it by the V, so I would take this side and divide it by that side, it will give me pretty much the exact same thing as doing the delta D divided by the R. Of course, the delta D is the change in the distance between the two locations. So those two things, those two ratios should be the same. So I've got my VP, I've got my VQ, and the difference between those two vectors is my change in V. I've got my radius over here, I've got my radius on the other side, and of course the difference between them would be my change in D, or displacement of my object. And the ratio between those two triangles needs to be the same because they're similar triangles. So what I can do is I can take those two things, I know they're going to be the same ratio, I can then use that in order to rearrange things a little bit, and I'll change that to an equal sign right there, and then I can rearrange and I can solve for my delta V. It would be the V delta D divided by R. Now this is really important because I've got a changing V. Like my V did change. Now the thing that's kind of different though is Usually when you guys think about a changing v, it's about going faster and slower, but velocity isn't just about how fast you're going, it's also about the direction. And the direction has changed. It's not the same velocity. It might be the same amount of speed, but the direction has changed. Therefore, the velocity has changed. Because velocity's got two parts to it, the speed part and the direction part. You change either one of those and the velocity has changed. And when you're going around a circle, your speed is constant. That can easily be constant, but your direction is always changing. So therefore, your velocity is always changing and you have a change in v. All right? Seems kind of weird, but that's just the way it is. So because we have a change in v, all right, so we have a change in v, we must have an acceleration. And the basic way to calculate acceleration, of course, is change in v over change in t. So if I take my expression for change in v, which is right here, my acceleration would be that expression we have, which is my change in v delta d divided by r, divided by time. And as soon as I do that, I've got two things go really nicely together. Delta d and delta t go very, very, very nicely together because d divided by t is just another speed. That is a little speed right there. So I've got speed multiplied by another speed and divided by r, which then becomes v squared divided by r. And that would be how to calculate the acceleration going in a circle. Now again, this is a very different acceleration expression than delta v divided by delta t, which is what you guys are used to. But again, remember, this acceleration is not about going faster or slower. It's about calculating a change in v based on change of direction. All right. So let's go to the next picture right there. Now this right here, this is what's often referred to as centripetal acceleration, which you've probably heard of before. And centripetal acceleration is called AC is v squared over r. Now, of course, acceleration is a vector. So it has magnitude, which the formula is great for, but it also has direction. And the direction of acceleration always points in the same direction as the change in velocity. So even the classic stuff you guys have done, if you've got a change in velocity and you have acceleration, these two things have to have the exact same direction no matter what. And if I go back to my picture, my change in v is pointing straight down between the two. Well, if I just take this vector and I move it where the actual object is, it would be over there. Okay, so the actual acceleration vector points in the same direction as the change in v vector. The change in v vector is actually pointing to the center of the circle. Okay, which seems kind of weird, but it's actually pointing to the middle. So this actually will, both of these actually, they actually point to the center of the circle. Now I'm going to get rid of this right here, and I'll draw it a different way, because if we go to basic classic vector subtraction, it would look a little bit different. So if I did basic change in v, of course, change in v is v2 minus v1. If I did that more like graphically, vq, this would be, I'm going to call it v2 and call it v1. If I drew these vectors the way you guys did it in grade 11, you know, we draw v2 would be going this way. That's fine. And then when I subtract v1, if I did like a tip to tail drawing for v1, I'd come this way. If I was adding v1, I would go up this way, but I'm not adding v1. I'm subtracting v1, which means it has to go the opposite direction, which means it would go this way. And again, the resultant vector, like you guys drew in grade 11, goes right to the middle of the circle. All right, so this whole change in v and acceleration actually point to the middle of the circle, which is what the last picture shows. So you've got these two things. You've got the velocity and you've got the acceleration, and these two are perpendicular to each other. And since the two are perpendicular to each other, this is why you're not going faster, you're not going slower. Okay, it's because they're perpendicular to each other. This is a right angle. Since they're perpendicular, the acceleration can't make it go faster, it can't make it go slower. All it does is change the actual direction. In order for it to make it go faster and slower, some of the acceleration has to be parallel to the v, but it's not. It's always perpendicular. And since it's always perpendicular, it can always just change the direction. So acceleration doesn't mean necessarily faster or slower. It means change in velocity, whether it's the speed part, which you guys are used to, or the direction part, which is what circular motion gives you. It doesn't matter. It's still going to be a relevant acceleration to the situation. If you go back to that little ladybug thing that I showed you previously and get the ladybug going around, there's a ladybug going around a circle. It's not speeding up, it's not slowing down, it is just going in a circle. Now I can show the velocity vector. There's my velocity vector for my little ladybug, always tangent to the circle. Okay, I can also show the acceleration vector. There's the acceleration vector. And you can see the acceleration vector is always pointing to the center. We can put both on there. There's both. And the two vectors are always perpendicular to each other no matter what. And since the velocity vector is always perpendicular, it doesn't make the ladybug go faster or slower. It just changes the direction. So that's one of the key differences between circular motion and all the other motion that you guys have done, is the two are always perpendicular. So it's always about changing the direction of the motion, not the speed of the motion. All right, and that's the basic fundamental idea behind centripetal acceleration.